Okay, so we've seen what a transfer function is, and it's going to be our main model of a system in this course, because we're going to be working with LTI systems, and obviously we're going to work in the frequency domain because things are much simpler there. Again, the definition of a transfer function is as the Laplace transform of the impulse response of the system. But typically when we're modeling systems, we'll come up with a differential equation. And from that differential equation, we can directly obtain the transfer function. So in fact, if we want to compute the impulse response, what we will typically do is actually find the transfer function first. And then use the transfer function, essentially invert the transfer function, find its inverse transform to get the impulse response. So as an example, let's take a simple circuit. Suppose we've got a so-called RC circuit consisting of a resistor and a capacitor. Let's call the voltage across these terminals V in. Excuse me. So we'll think of this as the input to our system, and we'll think of the voltage across the capacitor as the output. How do we find the transfer function? Well, we can do exactly the sort of thing we were doing when we were solving differential equations. The differential equation in this case, from circuit analysis, is RC times dV out by dt plus V out equals V in. So if we were going to solve this differential equation, we would simply take Laplace transforms. So let's do just that. And essentially look for the zero state response of the system. So to find the transform of the first term in terms of the transform of V out, we just apply our differentiation property of the Laplace transform. That tells us that the transform of the derivative of V out is S times V out of S minus the initial condition V out at 0 minus. Of course, the transform of V out is just V out of S, and likewise for V in. Okay. Now, the transfer function is the transform of the zero state response to a unit impulse. So if we were trying to find the impulse response in this fashion, we would set V out to 0. We would simply set V out to 0. We would set V in of S to be 1 because that's the transform of a unit impulse. And we would solve for V out of S, and that would have to be equal to our transfer function. To put it another way, what we could do is the following. Let's just solve for V out now. So V out of S is going to be 1 over SRC plus 1 times V in of S plus 1 over SRC plus 1 times V out of S. Sorry, times the initial condition V out of 0 plus, 0 minus. Okay. So, as we said before, This first term is the zero state response of the system, what we get when we set the initial conditions to 0. The second term is the so-called zero input response, which we get when we set v in of s to 0, and just find the response that results from initial conditions. So we're interested in the zero state response. So to get that, we simply set the initial conditions to 0, and doing so gives the zero state response. So in this case, it's V out of S equals 1 over SRC plus 1 times V in of S. So this is of the form Y of S equals H of S times F of S. And the H of S, in this case 1 over SRC plus 1, is our transfer function. This is the transfer function of the circuit. So, just to confirm, suppose V in is an impulse. So if V in of t is the unit impulse function, that means V in of S equals 1. That's the transform of unit impulse. And that means that V out of S is 1 over SRC plus 1. So 1 over SRC plus 1 is indeed the transform of the impulse response. If we set the initial conditions to 0 and make the input a unit impulse, we find that the transform of the response is 1 over SRC. So that's the transfer function. So to find transfer functions, which again are going to be the main models that we use, we can simply take a differential equation that models our system, apply Laplace transforms to all the terms of the equation, and set the initial conditions to 0. And in that way we can solve for the transfer function like this. So that's how we'll be getting transfer functions. So again, our main equation for the response of an LTI system in the frequency domain is going to take this form. So we're going to look at the response of such systems in the time domain, see what the time domain responses look like. We're also going to look at what we call the frequency response of an LTI system a little later. But to find the response in the time domain, we're essentially going to consider a couple of simple input signals. In principle, the response of a system is completely characterized by its response to unit impulses, but unit impulses are not always the easiest signal to generate in reality, in the lab or on a test bench. So we'll consider the responses to unit impulses and also to unit step functions. And then we'll look at examples of certain transfer functions. And we'll see that by considering just a couple of different examples, we will be able to extrapolate to much more complex transfer functions. This is one example that we're going to look at. This transfer function we call a first order transfer function because the order of the denominator polynomial is 1. The degree of the denominator polynomial is 1. So we call this a first order transfer function, or a first order system. That's essentially because our system was modeled by a first order differential equation. That's how we end up with a first order transfer function. But if we analyze the responses of first order and second order transfer functions, that will cover all of the cases that we really need to consider. Essentially because it will give us the cases of poles that are real valued. In this case, the pole of a transfer function is at s equals minus 1 over rc. And by looking at second order examples, we'll be able to look at the effect of complex valued poles on the responses of LTI systems. And when we've considered those two examples, we'll be able to extrapolate to much more complex HFSs and understand how LTI systems behave in the time domain. And again, that's really what systems and signals is all about, gaining an understanding of the input-output relationship of a system. So seeing what the responses of LTI systems are to a range of inputs. That's the sort of thing we need to do in order to solve engineering problems. So that's what we'll do for the next couple of lectures or so. See you in the next lecture.